Picture yourself standing on a mountaintop on the clearest night you can imagine. Stars stretch endlessly above you, galaxies swirling in cosmic dance, nebulae painting the darkness with ethereal light. You raise your hand toward the heavens, and in that simple gesture, you frame perhaps 1,000,000 stars between your thumb and forefinger. It feels infinite, doesn't it? But here's a question that might shake you to your core. What if everything you see, everything humanity has ever observed, every star, galaxy, and cosmic wonder visible to our most powerful telescopes, represents less than 5% of what actually exists? What if the universe you think you know is just the faintest whisper of an incomprehensibly vast reality? This isn't science fiction. This is the shocking truth that modern cosmology has revealed. When we ask how much of the universe is truly visible, we're not just questioning what our eyes can see or what our telescopes can detect. We're probing one of the most profound mysteries in all of science. The hidden cosmos that surrounds us, permeates us, and shapes everything we know, yet remains almost entirely invisible. Imagine the universe as a vast ocean, and everything we can see, everything that makes up the stars, planets, you, and me, is like the foam on top of a single wave. The rest, that hidden ocean, consists of two mysterious components that challenge our very understanding of reality: dark matter and dark energy. Together, they comprise about 95% of everything that exists. We are living, quite literally, in a cosmos that is mostly invisible. But visibility, as we'll discover, is far more complex and layered than you might think. Tonight, we're going to embark on an extraordinary journey through the seen and unseen universe. We'll start with what our eyes can perceive, venture into the realm of what our instruments reveal, and then plunge into the vast territories of the truly invisible. We'll explore how light itself becomes our cosmic messenger, carrying stories from the edge of space and time. We'll investigate the invisible scaffolding of dark matter that holds galaxies together, and the mysterious dark energy that's pushing the universe apart faster and faster. You'll discover that even the concept of visible shifts dramatically depending on where you stand in the cosmic hierarchy. What's visible to you on that mountaintop is a tiny fraction of what's visible to the Hubble Space Telescope, which in turn reveals only a small portion of what the James Webb Space Telescope can see, which itself captures merely a glimpse of what might truly be out there. As we journey deeper, we'll encounter mind-bending questions that will challenge everything you thought you knew about reality. Is the universe infinite? Are there regions so distant that their light will never reach us, no matter how long we wait? Could there be entire cosmic structures, maybe even other universes, that remain forever beyond our perception? And perhaps most unsettling of all, if 95% of the universe is invisible to us, what else might we be missing? By the time we return to that mountaintop, when you raise your hand toward the stars again, you'll understand that you're not just framing 1,000,000 points of light. You're touching the edge of an infinite mystery, one that reveals as much about the limits of human perception as it does about the boundless nature of existence itself. The story of cosmic visibility begins, surprisingly, with the very ordinary act of seeing. When you look up at that star-filled sky, photons that have traveled for years, sometimes centuries or millennia, are ending their cosmic journey by striking the retina in your eye. Each photon is a messenger, carrying information about the place and time of its birth. But here's where the story gets interesting.
What you see represents only the tiniest fraction of what's actually happening in the universe at any given moment. Your naked eye, remarkable as it is, can detect only about 6,000 stars under perfect conditions. That sounds like a lot until you realize that our galaxy alone contains somewhere between 100 billion and 400 billion stars. You're seeing roughly 0.00011% of just our local stellar neighborhood. It's like trying to understand the ocean by examining a single drop of water. The limitation isn't just numerical, it's fundamental. Human vision evolved to help us navigate a world illuminated by our sun, to distinguish between predator and prey, food and poison. Our eyes are exquisitely tuned to a narrow slice of the electromagnetic spectrum, what we call visible light, spanning wavelengths from about 380 to 700 nanometers. This represents less than 1% of the entire electromagnetic spectrum. It's as if the universe is broadcasting a symphony of information across countless radio stations, and we're tuned to just one channel. Think about what this means. Right now, as you read these words, you're being bombarded by radio waves from distant galaxies, infrared radiation from warm objects, ultraviolet light from hot stars, X-rays from black holes, and gamma rays from the most violent events in the cosmos. All of this invisible light is streaming through your body every second, carrying stories of cosmic birth and death, creation and destruction, yet you perceive none of it. But human ingenuity has allowed us to expand our cosmic senses. When Galileo first pointed his telescope at the night sky in 1609, he increased the visible universe by a factor that seemed infinite. Suddenly, the moon revealed mountains and craters, Jupiter showed 4 dancing moons, and the Milky Way resolved into countless individual stars. Each technological leap, from optical telescopes to radio arrays, from space-based observatories to gravitational wave detectors, has peeled back another layer of cosmic invisibility. The Hubble Space Telescope, launched in 1990, has arguably done more to expand human cosmic vision than any instrument since Galileo's first telescope. Free from the blurring effects of Earth's atmosphere, Hubble has revealed galaxies billions of light years away, showing us the universe as it existed when it was young. The famous Hubble Deep Field images, created by pointing the telescope at seemingly empty patches of sky for days at a time, revealed thousands of galaxies in regions where ground-based telescopes saw nothing but darkness. Then came the James Webb Space Telescope, which began operations in 2022 and throughout 2024 and 2025 has been revolutionizing our understanding of cosmic visibility. JWST operates primarily in the infrared spectrum, allowing it to see through cosmic dust clouds that block visible light and to observe the most distant galaxies in the universe. In 2025, JWST observations have revealed galaxies that formed just a few 100 million years after the Big Bang, showing us cosmic structures that are so distant their light has been traveling toward us for over 13 billion years. But even these technological marvels reveal only the tip of the cosmic iceberg. The most recent estimates suggest that all the ordinary matter in the universe, everything made of atoms, everything that can emit, absorb, or reflect light, constitutes only about 5% of the total cosmic inventory. This includes all the stars, all the gas clouds, all the planets, all the black holes, and yes, all the dark matter and dark energy we know must exist but cannot directly observe. This realization first dawned on astronomers in the 1930s, when a Swiss-American astronomer named Fritz Zwicky was studying the Coma Cluster, a group of over 1,000 galaxies held together by their mutual gravitational attraction. When Zwicky calculated the total mass of all the visible matter in the cluster and compared it to the gravitational force needed to hold the cluster together, the numbers didn't add up. The visible matter together, the numbers didn't add up. The visible matter could only account for 1/7 of the gravitational required. Something invisible, something that interacted gravitationally but not electromagnetically, had to be present in vast quantities. Zwicky called this mysterious component dark matter, not because it was black or shadowy, but because it didn't emit, absorb, or reflect light. It was matter that was literally dark to all forms of electromagnetic radiation. For decades, many astronomers hoped this was just an error in calculation or an incomplete understanding of gravity. But as more observations accumulated, from the rotation of galaxies to the patterns of cosmic microwave background radiation, the evidence for dark matter became overwhelming. Today we know that dark matter outweighs.
But dark matter is just the beginning of cosmic invisibility. In 1998, two independent teams of astronomers studying distant supernovae made a discovery that shocked the scientific world. They found that the expansion of the universe, which had been slowing down for billions of years due to the gravitational pull of matter, was actually speeding up. Something was pushing space itself apart, working against gravity on the largest scales. This mysterious component was dubbed dark energy, and it appears to make up about 70% of the universe. Unlike dark matter, which clumps together and helps form cosmic structures, dark energy seems to be smoothly distributed throughout space, becoming more dominant as the universe expands and matter becomes more dilute. The nature of dark energy remains one of the greatest puzzles in modern physics. It could be a property of space itself, a quantum field that fills the universe, or something even more exotic that we haven't yet imagined. So when we ask how much of the universe is truly visible, we're really asking about the nature of reality itself. The pie chart of cosmic composition is startling: about 70% dark energy, 25% dark matter, and only 5% ordinary matter. Of that 5% of ordinary matter, only a fraction is luminous, actively emitting light. Most ordinary matter exists as dark clouds of gas in intergalactic space, detectable only through its subtle effects on light passing through it. This means that the dazzling array of stars, galaxies, and nebulae that fill our telescopes and inspire our sense of cosmic wonder represent perhaps 1 or 2% of everything that exists. It's as if we're trying to understand a vast city by looking only at the streetlights, while the buildings, roads, and infrastructure remain invisible. The implications of this cosmic invisibility extend far beyond astronomy. They challenge our fundamental understanding of physics and force us to confront the limits of human perception and knowledge. We pride ourselves on being a species that has unlocked the secrets of the atom and mapped the human genome, yet we find ourselves surrounded by a universe that is 95% mystery. But the story of cosmic visibility is far from over. As we develop new instruments and new techniques, we continue to expand our perception of the cosmos. Gravitational wave detectors like LIGO have opened an entirely new window on the universe, allowing us to hear the collision of black holes and neutron stars. Neutrino detectors buried deep underground catch ghostly particles that stream through the Earth as if it weren't there, carrying information from the hearts of stars and the remnants of the Big Bang itself. Future missions promise to push the boundaries even further. The upcoming Euclid Space Telescope and the Nancy Grace Roman Space Telescope will map dark matter and dark energy with unprecedented precision. The extremely large telescope with its 40-meter mirror will probe deeper into space and time than ever before. Each new observation brings us closer to understanding the true nature of cosmic visibility and our place within the vast, mostly invisible universe. Standing on that mountaintop, looking up at the stars, you now understand that you're not just observing the universe, you're participating in humanity's greatest detective story. Every photon that reaches your eye is a clue. Every observation a piece of evidence in our ongoing investigation of cosmic reality. The visible universe, spectacular as it is, may be just the beginning of a far grander and more mysterious cosmos that awaits our discovery.
The concept of cosmic visibility becomes even more intricate when we consider the fundamental role that light plays as our cosmic messenger. Light, in all its forms across the electromagnetic spectrum, is essentially the only way we can gather information about the distant universe. With the recent exception of gravitational waves and neutrinos, nearly everything we know about cosmic objects comes from the electromagnetic radiation they emit, reflect, or absorb. But light itself imposes profound limitations on what we can see. Nothing can travel faster than light in a vacuum, approximately 300,000 kilometers per second. This cosmic speed limit means that when we look into space, we're automatically looking back in time. The light from the nearest star, Proxima Centauri, takes over 4 years to reach us. The light from the Andromeda Galaxy has been traveling for 2.5 million years. When the James Webb Space Telescope observes the most distant galaxies, it's seeing them as they existed over 13 billion years ago when the universe was just a fraction of its current age. This temporal aspect of cosmic observation creates a fascinating paradox. The farther we look into space, the further back in time we see, but also the less of the universe becomes visible to us. There exists something called the observable universe, a sphere centered on Earth with a radius of about 46.5 billion light-years. This might seem confusing at first. If the universe is only 13.8 billion years old, how can we see objects 46.5 billion light-years away? The answer lies in the expansion of space itself. While light has been traveling towards us for 13.8 billion years at most, the space between us and distant objects has been expanding during that entire journey. An object whose light has taken 13 billion years to reach us is now actually about 30 billion light-years away due to cosmic expansion. The most distant objects we can theoretically observe are now about 46.5 billion light-years from us, defining the edge of our observable universe. But here's where cosmic visibility becomes truly mind-bending. Beyond this observable horizon lies the unobservable universe. Light from objects beyond this boundary simply hasn't had enough time to reach us since the Big Bang. These regions are not just currently invisible, they are fundamentally unobservable given the finite age of the universe and the speed of light. We have no idea how much universe exists beyond our observable horizon. It could be twice the size of what we can see, or it could be infinite. Recent calculations by cosmologists suggest that if cosmic inflation theory is correct, the total universe might be at least 10 to the power of 23 times larger than our observable portion. To put this in perspective, if the observable universe were the size of a grain of sand, the total universe might be larger than Earth. The vast majority of reality remains forever beyond our perception, not due to technological limitations, but due to the fundamental structure of space and time itself. Even within our observable universe, vast regions remain effectively invisible due to various cosmic phenomena. Interstellar dust clouds can obscure entire sections of the galaxy, hiding star formation regions and distant stellar populations. These cosmic dust lanes, composed of tiny particles of carbon, silicon, and other elements forged in stellar furnaces, act like cosmic fog, absorbing and scattering visible light while allowing infrared radiation to pass through relatively unimpeded. The center of our own galaxy remained largely invisible to optical telescopes for centuries due to dense dust clouds along the galactic plane. Only with the development of infrared and radio astronomy did we discover the supermassive black hole that lurks at the Milky Way's heart, now known as Sagittarius A. In 2022 and continuing through 2025, the Event Horizon Telescope collaboration has provided increasingly detailed images of this invisible giant, revealing the shadow of the black hole's event horizon against the glowing material falling into it. Black holes themselves represent perhaps the ultimate cosmic invisibility. By definition, nothing can escape from within their event horizons, not even light. They reveal themselves only through their gravitational effects on nearby matter and the brilliant accretion disks of materials spiraling into them. Yet, black holes may be far more common than we realize. Recent estimates suggest that our galaxy contains approximately 100 million stellar mass black holes, most of which remain completely invisible unless they happen to have a companion star feeding them material. Rogue planets, ejected from their birth systems and wandering through interstellar space, represent another form of cosmic invisibility. These orphaned worlds, some perhaps larger than Jupiter, drift through the galaxy in darkness, neither generating their own light like stars, nor reflecting light from a parent star. Microlensing surveys have begun to detect these cosmic wanderers when they pass between us and distant stars, briefly magnifying the starlight through gravitational lensing. Current estimates suggest there might be billions of rogue planets in our galaxy alone, an entire hidden population of worlds drifting silently through the void. The cosmic web itself, the largest structure in the universe, remains largely invisible despite spanning billions of light years. This web consists of vast filaments of dark matter and gas connecting galaxies and galaxy clusters across cosmic distances. While we can computer simulate the web structure and we can infer its presence from the distribution of galaxies, most of the filaments themselves remain too faint to observe directly. Recent work with the Cosmic Web Imager and similar instruments has begun to reveal some of these structures, but we've likely seen only a tiny fraction of this cosmic scaffolding.
Even more exotic forms of invisible matter might exist. Theoretical physics predicts the possible existence of shadow matter or mirror matter, entire parallel sectors of particles that interact gravitationally but not electromagnetically with ordinary matter. If such shadow sectors exist, there could be shadow stars, shadow planets, even shadow life forms existing alongside our visible universe, completely undetectable except through their gravitational influence. The quantum vacuum itself, the empty space between particles, seeds with invisible activity. Virtual particles constantly pop into existence and annihilate each other on timescales so brief they seem to violate conservation of energy, permitted only by Heisenberg's uncertainty principle. This vacuum energy might be related to dark energy, the mysterious force driving cosmic acceleration, though the predicted values differ from observations by an embarrassing factor of 10 to the power of 120, perhaps the worst prediction in the history of physics. Neutrinos represent another form of cosmic invisibility that we're only beginning to understand. These ghostly particles, produced in vast numbers by nuclear reactions in stars and during supernovae, barely interact with ordinary matter. Trillions of neutrinos stream through your body every second without you feeling a thing. The sun produces so many neutrinos that even though they rarely interact with matter, about 65 billion solar neutrinos pass through every square centimeter of your body every second. Underground neutrino detectors like the Super Kamikonde in Japan and IceCube in Antarctica have opened a new window on cosmic invisibility, detecting neutrinos from the sun, from cosmic ray interactions in Earth's atmosphere, and even from distant supernovae. In 2025, next-generation neutrino telescopes are beginning to map the neutrino sky, revealing a universe that looks completely different when viewed through these ghostly messengers. Gravitational waves represent perhaps the newest form of cosmic invisibility, detected for the first time in 2015 by the Laser Interferometer Gravitational Wave Observatory. These ripples in spacetime itself, predicted by Einstein over a century ago, allow us to observe cosmic events that produce no electromagnetic radiation whatsoever. The collision of two black holes, invisible in all forms of light, rings spacetime like a bell, creating gravitational waves that carry information about these cosmic cataclysms across billions of light years. The LIGO Virgo Cagra detector network has now observed dozens of black hole mergers and several neutron star collisions, opening an entirely new field of gravitational wave astronomy. These observations reveal a universe filled with invisible events. Black hole mergers happen far more frequently than anyone expected, suggesting that the cosmos is even more violent and dynamic than our electromagnetic observations suggested. Future gravitational wave detectors, including the proposed space-based LISA mission and next-generation ground-based detectors, will be sensitive to gravitational waves from the early universe itself, potentially revealing cosmic events from the first moments after the Big Bang. These observations might detect the gravitational wave background from cosmic inflation, providing our first direct evidence of what happened in the universe's first fraction of a second. But perhaps the most profound form of cosmic invisibility relates to the fundamental nature of space and time themselves. Einstein's general relativity tells us that gravity is not a force, but the curvature of space-time itself.
massive objects bend the fabric of space and time, creating what we perceive as gravitational attraction. This curvature itself is invisible. We can observe its effects on matter and light, but we cannot directly see the warping of space-time. On quantum scales, the very concepts of position and velocity become fuzzy due to Heisenberg's uncertainty principle. Particles exist in quantum superposition states, occupying multiple positions simultaneously until observed. The quantum world operates according to probability rather than certainties, suggesting that reality itself might be fundamentally invisible until we interact with it through measurement. These quantum effects might extend to cosmic scales through various proposed theories. Some interpretations of quantum mechanics suggest that parallel universes split off with every quantum measurement, creating an infinite multiverse where every possible outcome occurs in some branch of reality. These parallel universes would be completely invisible to us, forever beyond our reach, yet intimately connected to our own cosmic branch. String theory, one attempt to unify quantum mechanics with general relativity, proposes that reality consists of vibrating strings in 11-dimensional space. The extra dimensions, beyond our familiar 3 spatial dimensions plus time, are curled up so small that we cannot perceive them directly. If string theory is correct, most of reality exists in these invisible extra dimensions, with our entire visible universe confined to a 3-dimensional slice of a much larger hyperdimensional space. The cosmic microwave background radiation, the afterglow of the Big Bang itself, provides another window into cosmic invisibility. Discovered accidentally in 1965, fills the entire universe and carries information about conditions when the cosmos was only 380,000 years old. Before this time, the universe was opaque to light, filled with a hot plasma that absorbed and scattered photons. The period before the cosmic microwave background represents a form of temporal invisibility. We cannot see electromagnetic radiation from the universe's first 380,000 years. Recent observations of the cosmic microwave background by satellites like Planck have revealed subtle patterns that encode information about the universe's composition, geometry, and early history. These measurements confirm that ordinary matter makes up only 5% of the cosmic total, with dark matter and dark energy comprising the rest. The precision of these measurements is extraordinary. We can now determine the universe's age to within 1% and its geometry to incredible accuracy. Yet even these remarkable observations leave vast questions unanswered. The cosmic microwave background shows us the universe at a single moment in cosmic history when it first became transparent to light. What happened before this moment remains largely invisible to electromagnetic observation, accessible only through theoretical physics and the subtle signatures left in the cosmic microwave background. Cosmic inflation, the rapid expansion that supposedly occurred in the universe's first fraction of a second, might have left gravitational wave signatures that future detectors could observe. If detected, these primordial gravitational waves would provide our first direct evidence of cosmic inflation and might reveal physics at energy scales far beyond anything achievable in terrestrial particle accelerators. The question of cosmic visibility also extends to the possibility of life elsewhere in the universe. Even if life is common in the cosmos, it might remain largely invisible to our current detection methods. Microbial life would be nearly impossible to detect beyond our solar system, and even complex ecosystems might leave only subtle signatures in the atmospheres of distant exoplanets. The search for extraterrestrial intelligence has been ongoing for decades, listening for radio signals that might indicate technological civilizations. But advanced civilizations might communicate with methods we haven't yet discovered, or might deliberately avoid sending signals that could be detected by younger civilizations like ourselves. They might exist in forms of cosmic invisibility that we cannot yet imagine. Even closer to home, life might exist in environments we consider invisible or inaccessible. The subsurface oceans of Jupiter's moon Europa and Saturn's moon Enceladus might harbor entire ecosystems beneath kilometers of ice. These alien biospheres would be completely hidden from surface observation, detectable only through careful analysis of the chemistry of water plumes ejected into space.
The concept of astrobiology has expanded to consider life in environments that would have seemed impossible just decades ago. In the upper atmospheres of gas giants, in the interiors of asteroids, or even in the vacuum of space itself. If life can exist in such extreme environments, it might be far more common than we realize, yet remain largely invisible to our current detection methods. Looking toward the future,
Our expanding technological capabilities promise to reveal new forms of cosmic visibility while simultaneously highlighting the vast territories that remain hidden. The James Webb Space Telescope, operating primarily in infrared wavelength, has already begun to peer through cosmic dust clouds and observe the most distant galaxies in the universe. Throughout 2024 and 2025, JWST has revealed galaxies that formed just a few 100 million years after the Big Bang, showing us cosmic structures that are more massive and organized than theoretical models predicted. These observations are forcing astronomers to reconsider their understanding of early cosmic evolution. The invisible universe of the past, revealed through JWST's time machine-like observations, appears to have been more dynamic and complex than we imagined. Star formation began earlier and proceeded more rapidly than expected, suggesting that the invisible processes of cosmic evolution operated differently in the universe's youth. Ground-based telescopes are also pushing the boundaries of cosmic visibility. The extremely large telescope, currently under construction with a 40-meter primary mirror, will have unprecedented resolution and light-gathering power. When it begins operations later this decade, it will be able to directly image Earth-sized exoplanets around nearby stars and analyze their atmospheres for signs of life. Radio astronomy continues to expand our perception of cosmic invisibility through projects like the Square Kilometer Array, which will be the most sensitive radio telescope ever built. This instrument will be able to detect radio signals from hydrogen gas in the most distant galaxies, mapping the large-scale structure of the universe in unprecedented detail, and potentially revealing cosmic phenomena that remain invisible to other forms of observation. Yet with each new discovery, we also become more aware of what remains hidden. The dark sector of the universe, dark matter and dark energy, continues to resist direct detection despite decades of increasingly sophisticated experiments. Underground laboratories around the world house detectors designed to catch dark matter particles, but so far, these invisible components of cosmic reality remain stubbornly undetected. The nature of dark energy remains even more mysterious. Whether it represents a fundamental property of space itself, a dynamic quantum field, or something even more exotic, dark energy appears to be the dominant component of reality, yet remains almost completely invisible to our attempts at direct observation. Its effects on cosmic expansion are clear, but its fundamental nature remains one of the greatest puzzles in science. As we stand on the threshold of a new era in cosmic observation, we must grapple with the humbling realization that the vast majority of the universe remains invisible to us. This cosmic invisibility is not merely a technological limitation that better instruments might overcome. It appears to be a fundamental feature of reality itself, built into the very structure of space, time, and matter. The journey through cosmic visibility reveals layers upon layers of hidden reality, from the dark matter that outweighs ordinary matter by 5-to-1, to the dark energy that dominates cosmic evolution, to the vast regions beyond our observable horizon that remain forever inaccessible. Each revelation about cosmic invisibility simultaneously expands our understanding and humbles us with the recognition of how much remains unknown. Standing beneath that star-filled sky, you now understand that the universe visible to your eyes, beautiful and inspiring as it is, represents only the faintest whisper of cosmic reality. The true universe, in all its invisible majesty, surrounds you like an infinite ocean, mostly hidden from perception, yet intimately connected to everything you see and experience. This cosmic invisibility is not a barrier to understanding, but an invitation to wonder, a reminder that reality is far stranger and more magnificent than our limited senses can perceive. As we delve deeper into the cosmic mystery, we encounter phenomena that challenge not just what we can see, but how we define visibility itself. The universe operates across scales so vast and mechanisms so subtle that our everyday concepts of observation and detection begin to break down. Consider the cosmic web, the largest known structure in the universe, stretching across billions of light years like an inconceivably vast spider's web made of dark matter and tenuous gas. This cosmic web consists of filaments, nodes, walls, and voids that define the architecture of reality on the grandest scales. Galaxies are not randomly scouted through space, but follow these invisible pathways, clustering along filaments like dewdrops on morning spider silk. Most of the structure remains invisible because the gas within the filaments is so thin,
often less than 1 atom per cubic meter, that it emits almost no detectable light. Yet recent technological advances have begun to reveal glimpses of this hidden cosmic architecture. In 2019, astronomers using the Cosmic Webb Imager detected fluorescent emission from gas filaments connecting galaxies across millions of light years. The gas was glowing faintly in response to the ultraviolet background radiation that permeates the universe, like cosmic streetlights illuminating an otherwise invisible interstate highway system. The 2024 and 2025 observations with improved instruments have revealed more of these cosmic filaments, showing that they contain a significant fraction of the universe's ordinary matter. Previous surveys had found that when astronomers added up all the matter they could observe in stars, galaxies, and gas clouds, they came up short. About half of the ordinary matter predicted by Big Bang models seemed to be missing. The cosmic web appears to be where much of this missing matter has been hiding, too diffuse and cool to be easily detected, but substantial enough to shape cosmic evolution. This raises profound questions about cosmic visibility and the nature of discovery itself. How much of the universe consists of phenomena that are technically detectable but practically invisible due to their subtlety? The cosmic web existed for billions of years before we developed instruments sensitive enough to see it. What other cosmic structures surround us right now, waiting for the next generation of technology to reveal them? Dark matter presents an even more fundamental challenge to our understanding of cosmic visibility. Unlike ordinary matter, which can emit, absorb, or scatter light under the right conditions, dark matter appears to interact only gravitationally. It doesn't participate in electromagnetic interactions at all, making it invisible not just to our eyes, but to every form of electromagnetic radiation across the entire spectrum. Yet dark matter's gravitational effects are unmistakable and profound. Galaxy rotation curves, measurements of how fast stars orbit within galaxies, provided some of the first convincing evidence for dark matter's existence. Without dark matter's additional gravity, galaxies would spin themselves apart. The outer regions of galaxies rotate much faster than they should if only the visible matter were providing gravitational binding. Computer simulations of cosmic evolution, run with and without dark matter, revealed dramatically different outcomes. Without dark matter, the universe would lack the gravitational scaffolding necessary to build the complex structures we observe today. The tiny density fluctuations in the early universe, visible in the cosmic microwave background, would never have grown into the rich hierarchy of cosmic structures, from the smallest dark matter halos to the largest galaxy clusters that we see today. Dark matter might constitute entire parallel ecosystems of invisible particles. The simplest models assume dark matter consists of a single type of particle, perhaps weakly interacting massive particles, or WIMPs. But more complex models propose rich dark sectors, with multiple types of dark matter particles, dark forces mediating interactions between them, and potentially even dark atoms, dark molecules, and dark chemistry occurring in parallel to our visible universe.
If such complex dark sectors exist, there might be dark planets orbiting dark stars, powered by dark fusion reactions and supporting dark life forms that remain forever invisible to electromagnetic observation. These dark civilizations, if they exist, would occupy the same space as our visible universe, but remain as inaccessible to us as we would be to them, two cosmic ghost towns passing through each other without interaction. The search for dark matter has spawned increasingly sophisticated detection efforts. Deep underground laboratories house detectors designed to catch the rare interactions between dark matter particles and ordinary matter. These experiments, with names like Xenon, Lux Zeppelin, and Pico, represent humanity's attempt to make the invisible visible through direct particle detection. So far, these searches have yielded tantalizing hints, but no definitive detection. Several experiments have reported anomalous signals that could indicate dark matter interactions, but these results remain controversial and unconfirmed. The failure to directly detect dark matter particles after decades of increasingly sensitive searches has led some physicists to propose alternative explanations for the observations attributed to dark matter. Modified gravity theories suggest that our understanding of gravity itself might be incomplete. Perhaps gravity behaves differently on galactic scales than Einstein's general relativity predicts, eliminating the need for dark matter altogether.
These theories, with names like modified Newtonian dynamics or MOND, can explain some observations attributed to dark matter but struggle to account for others, particularly the detailed patterns in the cosmic microwave background. The cosmic microwave background provides perhaps the strongest evidence for dark matter's existence. The precise patterns of hot and cold spots in this radiation encode a detailed record of conditions in the early universe. These patterns can only be explained if dark matter was present to provide the gravitational scaffolding for structure formation. Alternative gravity theories have difficulty reproducing these observations with the same precision as dark matter models. Yet even if dark matter exists as predicted, its ultimate nature remains one of physics' greatest mysteries. Dark matter particles, if they exist, must have properties unlike any particles in the standard model of particle physics. They must be stable over cosmic timescales, interact only weakly with ordinary matter, and have masses that could range from nearly 0 to many times the mass of a proton. The Large Hadron Collider and other particle accelerators have searched for dark matter by trying to create it in high-energy collisions. If dark matter particles can be produced and detected in laboratory conditions, it would provide the first direct evidence of their existence and reveal their properties. So far, these searches have placed increasingly stringent limits on possible dark matter interactions, but have not achieved a confirmed detection. Meanwhile, dark energy presents an even greater challenge to our understanding of cosmic visibility. Unlike dark matter, which can be mapped through its gravitational effects on visible matter, dark energy reveals itself only through its influence on the expansion of space itself. This makes it the most invisible component of the universe. It cannot be concentrated, collected, or directly manipulated by any known means. The discovery of dark energy came from observations of distant supernovae, cosmic explosions so bright they can be seen across billions of light years. Type A supernovae in particular serve as cosmic standard candles because they always explode with approximately the same intrinsic brightness. By comparing their apparent brightness with their redshift, how much the expansion of space has stretched their light, astronomers can measure the history of cosmic expansion. The shocking discovery was that cosmic expansion is accelerating. For the first 9 billion years after the Big Bang, gravity gradually slowed the expansion as expected. But about 5 billion years ago, something changed. The expansion began to speed up, as if some anti-gravitational force was pushing space apart faster and faster. This acceleration appears to be driven by dark energy, a component that makes up about 70% of the total cosmic energy density. Unlike matter, which becomes more dilute as the universe expands, dark energy maintains a constant density, even as space grows. This means that as the universe expands, the total amount of dark energy increases, making it increasingly dominant over matter and driving ever faster expansion. The nature of dark energy remains completely mysterious. The simplest explanation is that it represents a cosmological constant, a fundamental property of space itself. Einstein actually introduced such a constant in his equations of general relativity to allow for a static universe, but he later abandoned it when Hubble discovered cosmic expansion. Ironically, the cosmological constant might be the correct explanation for dark energy, though Einstein probably never imagined it would drive accelerating expansion rather than static equilibrium. If dark energy is indeed a cosmological constant, it raises profound questions about the nature of space and quantum mechanics. Quantum field theory predicts that empty space should be filled with zero-point energy from quantum fluctuations. But when physicists calculate the expected energy density of the quantum vacuum, they get a result that exceeds the observed dark energy density by a factor of 10 to the power of 120. This cosmological constant problem represents perhaps the worst prediction in the history of science. Alternative explanations for dark energy include quintessence fields, dynamic quantum fields that vary in space and time, or modifications to general relativity that change how gravity behaves on cosmic scales. Some theories propose that dark energy is not a fundamental component, but an emergent property arising from the complex interplay of matter and space on cosmic scales. Others suggest that our observations of acceleration might be artifacts of our particular location in the universe, or systematic errors in our understanding of cosmic distances. The implications of dark energy for cosmic visibility extend far into the future. If dark energy continues to drive accelerating expansion, the universe will enter a phase called the Big Rip, where space expands so rapidly that it overcomes all other forces. Eventually, dark energy would tear apart galaxies, solar systems, atoms, and even subatomic particles themselves. Long before this extreme scenario, accelerating expansion would push distant galaxies beyond our observable horizon, making more and more of the universe invisible as time passes. Alternatively, dark energy might not be constant. If it strengthens over time, the Big Rip could occur in as little as 20 billion years. If it weakens, cosmic expansion might eventually slow down again, potentially leading to a big crunch where the universe collapses back on itself. Some models propose that dark energy could even become negative, causing space itself to contract and bringing distant regions of the universe back into visibility. Future dark energy surveys aim to map the expansion history of the universe with unprecedented precision. Projects like the Dark Energy Survey, the Dark Energy Spectroscopic Instrument, and the upcoming Euclid and Roman space telescopes will measure the distances and redshifts of millions of galaxies, creating three-dimensional maps of cosmic structure and tracking how dark energy has influenced cosmic evolution over billions of years. These observations might reveal whether dark energy is truly constant or whether it evolves over cosmic time. They might detect subtle signatures of alternative gravity theories or evidence for extra dimensions of space. Most importantly, they might provide clues about the fundamental nature of space, time, and quantum mechanics that govern cosmic visibility on the largest scales. The search for cosmic visibility also extends to the very boundaries of the observable universe itself. The cosmic microwave background represents the most distant electromagnetic radiation we can observe, but it's not the absolute edge of cosmic visibility. Gravitational waves and neutrinos can travel from even earlier epochs, potentially carrying information from the first moments after the Big Bang.
Primordial gravitational waves, generated during cosmic inflation in the universe's first fraction of a second, might still be detectable today as a subtle pattern in the polarization of the cosmic microwave background. The Bicep and Planck experiments have searched for these signals, representing humanity's attempt to observe the universe when it was less than a trillionth of a trillionth of a trillionth of a second old. Such observations would provide direct evidence for cosmic inflation and might reveal physics at energy scales billions of times higher than anything achievable in terrestrial particle accelerators. They would extend cosmic visibility back to the very moment of cosmic birth, revealing conditions when the entire observable universe was smaller than a subatomic particle. Neutrino astronomy offers another window into cosmic invisibility. The universe is filled with a background of neutrinos left over from the Big Bang, similar to the cosmic microwave background but consisting of particles rather than photons. These relic neutrinos, produced when the universe was only 1 second old, should still be detectable today, though their extremely low energies make direct detection extraordinarily challenging. Future neutrino detectors might be sensitive enough to observe this cosmic neutrino background, providing yet another view of the early universe. Neutrinos interact so weakly with matter that they can escape from the cores of supernovae and carry information about conditions inside these cosmic explosions that no other form of radiation can reveal. The IceCube Neutrino Observatory, buried in the Antarctic ice, has already detected high-energy neutrinos from distant galaxies, opening the field of neutrino astronomy. These observations reveal cosmic accelerators operating at energies far beyond anything humans can create, probably involving supermassive black holes or other extreme cosmic phenomena that remain largely invisible to electromagnetic observation. As we push the boundaries of cosmic visibility, we also confront fundamental limits imposed by the nature of reality itself. Quantum mechanics suggests that space and time might not be continuous but rather discrete, made up of indivisible units called Planck lengths and Planck times. If true, these quantum scales represent the ultimate limit of cosmic visibility. Below the Planck scale, the very concepts of space and time break down. String theory and other attempts to unify quantum mechanics with general relativity propose that reality consists of additional spatial dimensions beyond the three we can perceive.
These extra dimensions might be curled up so small that we cannot access them directly, or they might be large but accessible only to gravitational forces. If such dimensions exist, most of reality would remain invisible to us, confined as we are to our three-dimensional slice of a higher dimensional space. Some theories propose that our entire universe might be a hologram, a three-dimensional projection of information encoded on a two-dimensional surface. The holographic principle suggests that all the information contained within any region of space can be represented by information on the boundary of that region. If true, cosmic visibility might be fundamentally illusory. The three-dimensional space we perceive might be a projection of more fundamental processes occurring in fewer dimensions. These ideas challenge our most basic assumptions about the nature of reality and observation. If the universe is holographic, then the question of cosmic visibility becomes not just what we can see, but whether what we see represents the fundamental level of reality or merely a shadow of deeper processes that remain forever hidden from direct observation. The multiverse hypothesis adds yet another layer to cosmic invisibility. If cosmic inflation is correct, our observable universe might just be one bubble in an infinite foam of universes, each with potentially different physical laws and fundamental constants. These other universes would be completely invisible to us, separated by regions of space expanding faster than light. Within the context of the multiverse, the question of cosmic visibility takes on new meaning. Our visible universe, vast as it is, might represent an infinitesimally small fraction of total reality. The multiverse might contain universes where dark matter behaves differently, where dark energy doesn't exist, or where the fundamental forces have different strengths. Some universes might be more visible than ours, while others might be even more dominated by invisible components. The anthropic principle suggests that we observe the particular cosmic properties we do because they're necessary for the existence of observers like ourselves. In universes where most matter was visible, galaxies might never have formed, stars might never have ignited, or planets might never have developed conditions suitable for life. We live in a universe with the particular balance of visible and invisible components necessary for cosmic evolution to produce complexity and consciousness. This anthropic reasoning might explain why so much of our universe is invisible. Perhaps universes where most matter is visible are unstable or fail to develop the hierarchical structures necessary for life. The cosmic invisibility we observe might be a prerequisite for our own existence, a necessary feature of any universe complex enough to evolve observers capable of questioning their own cosmic visibility. Recent developments in theoretical physics have proposed even more exotic forms of cosmic invisibility. Axions, hypothetical particles proposed to solve certain problems in quantum cluidodynamics, might make up some or all of dark matter. Unlike WIMPs, axions would interact with electromagnetic fields under certain conditions, potentially making them detectable through carefully designed experiments that convert axions to photons in strong magnetic fields. The Axion Dark Matter Experiment and similar project represent humanity's attempt to make these invisible particles visible through quantum conversion processes. If successful, such experiments would not only detect dark matter, but reveal a new type of particle physics operating throughout the cosmos. Sterile neutrinos, hypothetical particles that interact even more weakly than ordinary neutrinos, might comprise another component of cosmic invisibility. These particles would be almost impossible to detect directly, but might reveal themselves through their subtle effects on cosmic structure formation or through their decay products in certain environments. The possibility of primordial black holes adds another dimension to cosmic invisibility. These hypothetical objects, formed from density fluctuations in the early universe rather than stellar collapse, could range in mass from less than an asteroid to millions of solar masses. Primordial black holes would be essentially invisible except for their gravitational effects, and they might comprise some fraction of dark matter. Recent observations by gravitational wave detectors have revealed the existence of black holes with unexpected masses and properties, raising the possibility that some of these objects might be primordial rather than stellar in origin. Future gravitational wave observations might reveal the signature of primordial black hole formation or the merger of these invisible cosmic fossils from the early universe. The concept of cosmic visibility also extends to the possibility of detecting evidence for cosmic civilizations that might exist elsewhere in the universe. advanced technological civilizations might engineer structures or processes that would be detectable across interstellar or even intergalactic distances. Dyson spheres, hypothetical megastructures built around spars to capture their energy output, would appear as infrared sources with unusual spectral properties. Freeman Dyson originally proposed these structures in 1960 as a natural development for energy-hungry civilizations. A Dyson sphere would make its host star partially or completely invisible in visible light, while glowing brightly in infrared radiation.
Other potential technosignatures include artificial illumination on the night sides of exoplanets, atmospheric pollution from industrial activity, or the waste heat from massive computational projects. Advanced civilizations might even leave signatures in the cosmic microwave background itself if they engaged in universe-scale engineering projects during the early epochs of cosmic history. The search for extraterrestrial intelligence has expanded beyond traditional radio searches to include optical SETI, looking for brief laser pulses from distant civilizations, and even searches for evidence of stellar engineering. These efforts recognize that cosmic civilizations might remain invisible to us, not because they don't exist, but because we haven't yet learned to recognize the signatures of their technology. The question of cosmic visibility ultimately forces us to confront the limits of knowledge itself. As we've seen, the vast majority of the universe appears to be invisible to electromagnetic observation. Dark matter and dark energy dominate cosmic evolution, yet resist direct detection. Regions beyond our observable horizon remain forever inaccessible. Quantum mechanics suggests that reality itself might be fundamentally probabilistic rather than deterministic. These limitations are not merely technological challenges that better instruments might overcome. They appear to be built into the fundamental structure of reality itself. The speed of light limit means that distant regions will always remain invisible to us. The quantum nature of matter and energy means that perfect knowledge of any system is impossible. The expansion of space means that more and more of the universe disappears beyond our observable horizon with each passing moment. Yet these limits also inspire rather than constrain human curiosity. Each boundary we encounter reveals new questions and new possibilities for discovery. The recognition that 95% of the universe is invisible has sparked an explosion of creativity in theoretical physics and observational astronomy. Scientists have proposed exotic new particles, extra dimensions, holographic realities, and multiverse scenarios that would have seemed like pure fantasy just decades ago. The invisible universe challenges us to expand our definition of observation and knowledge. If we cannot see dark matter directly, we can map its distribution through gravitational lensing. If dark energy resists direct detection, we can trace its effects through precision measurements of cosmic expansion. If quantum mechanics prohibits perfect knowledge, we can work with probabilities and statistical ensembles to understand cosmic behavior. Future technologies promise to push the boundaries of cosmic visibility even further. Gravitational wave astronomy, barely a decade old, will expand dramatically as new detectors come online. The planned LISA space-based detector will be sensitive to gravitational waves from supermassive black hole mergers across cosmic distances, potentially observing events from the very early universe. Next-generation neutrino detectors will map the universe through these ghostly particles, revealing cosmic phenomena invisible to electromagnetic observation. Radio telescopes like the Square Kilometre Array will map hydrogen gas throughout cosmic history, tracing the evolution of galaxies and large-scale structure with unprecedented detail. The James Webb Space Telescope continues to revolutionize our understanding of cosmic visibility by observing the universe in infrared wavelengths. Throughout 2024 and 2025,
JWST has revealed galaxies that formed when the universe was only a few 100 million years old, showing us cosmic structures that challenge our understanding of early cosmic evolution. These observations suggest that galaxy formation began earlier and proceeded more rapidly than theoretical models predicted. The invisible processes that shaped the early universe appeared to have been more efficient at building cosmic structures than we realized. Future observations with JWST and other next-generation telescopes will continue to push back the boundaries of cosmic time, revealing more of the invisible history of cosmic evolution. Advances in computational cosmology allow scientists to simulate the invisible universe with increasing realism. Modern supercomputers can model the evolution of dark matter and dark energy across billions of years, creating virtual universes that can be compared with observations. These simulations reveal the invisible cosmic web in exquisite detail, showing how dark matter flows along vast filaments and accumulates in dense nodes where galaxies form. The Millennium simulation and its successors have created detailed maps of how cosmic structures grow under the influence of dark matter and dark energy. These computational universes allow scientists to explore cosmic visibility by predicting what observations should reveal and comparing these predictions with real data from telescopes and other instruments. Machine learning and artificial intelligence are also revolutionizing our ability to extract information from cosmic observations. AI algorithms can identify subtle patterns in vast datasets that might escape human notice, potentially revealing new forms of cosmic visibility hidden in the noise of observational data. Deep learning networks trained on cosmological simulations can classify galaxy types, identify gravitational lenses, and even predict the properties of dark matter halos from limited observational data. These tools represent a new form of cosmic visibility, allowing us to infer the properties of invisible cosmic components through sophisticated statistical analysis of visible phenomena. As we develop new ways to observe and understand the invisible universe, we also grapple with philosophical questions about the nature of reality and knowledge. If most of the universe is invisible to us, what does this say about the relationship between observation and existence? Do dark matter and dark energy exist in the same sense as the matter and energy we can observe directly? These questions echo ancient philosophical debates about the nature of reality and perception. Plato's allegory of the cave suggested that what we perceive as reality might be merely shadows cast by true reality onto the walls of our perceptual prison. The modern cosmic discovery that 95% of the universe is invisible gives new relevance to these ancient insights. The invisible universe also challenges our understanding of cosmic evolution and our place within it. If dark matter and dark energy dominate cosmic development, then the visible matter that makes up stars, planets, and life represents a small perturbation on much larger invisible processes. We exist within cosmic structures shaped primarily by invisible forces, orbiting a star powered by nuclear processes that are themselves manifestations of invisible quantum fields. Yet, this cosmic humility might also be empowering. The recognition that we are embedded within vast invisible realities greater than ourselves connects us to something transcendent and magnificent. We are not separate from the cosmic invisibility, but part of it, composed of atoms forged in stellar furnaces that are themselves embedded within vast dark matter halos. The water in your body, the calcium in your bones, the iron in your blood, all were created inside stars and dispersed through space by supernova explosions billions of years ago. You are literally made of star stuff, connected to cosmic processes operating across vast scales of space and time. The invisible cosmic web that shapes galaxy formation also shapes the chemical elements that make up your body. This cosmic perspective transforms the question of visibility from a purely scientific concern to a deeply personal and philosophical one. When you look up at the night sky, you're not just observing distant lights, but contemplating your own cosmic origins and destiny. The invisible universe surrounds you and flows through you, connecting you to cosmic processes that began shortly after the Big Bang and will continue long after the sun died. The future of cosmic visibility holds extraordinary promise for expanding human understanding and perspective. As our instruments become more sensitive and our theoretical understanding deepens, we will undoubtedly discover new forms of cosmic invisibility that we cannot yet imagine. Each generation of astronomers has been surprised by the richness and strangeness of cosmic reality revealed by their observations. The generation that discovered galaxies beyond our own was astounded by the scale of the universe. The generation that discovered cosmic expansion was amazed by the dynamic nature of space itself. The generation that discovered dark matter and dark energy was shocked by the invisible domination of cosmic evolution. Future generations will likely be equally surprised by discoveries we cannot yet anticipate.
Perhaps we will directly detect dark matter particles and discover a rich physics of dark interactions that parallels our own electromagnetic world. Perhaps we will understand the nature of dark energy and learn to manipulate the expansion of space itself. Perhaps we will detect gravitational waves from cosmic inflation and observe the universe when it was smaller than an atom. Or perhaps we will discover that our current understanding of cosmic invisibility is fundamentally incomplete, that reality operates according to principles we have not yet imagined. The history of science suggests that our most profound discoveries often come not from confirming our expectations, but from recognizing how wrong our assumptions have been. The invisible universe reminds us that reality is far stranger and more wonderful than our limited senses can perceive. It challenges us to expand our concept of existence beyond the narrow band of electromagnetic radiation that defines human vision. It invites us to imagine forms of cosmic reality that operate according to principles we are only beginning to understand. Standing beneath that star-filled sky, contemplating the cosmic invisibility that surrounds you, you become part of humanity's greatest adventure, the quest to understand the nature of reality itself. The visible stars above you are just the beginning of the story. The true universe, in all its invisible majesty, awaits our discovery. As we stand at the threshold of new cosmic revelations, the very definition of visibility continues to evolve. What seemed permanently invisible to one generation becomes observable to the next through technological innovation and theoretical insight. The cosmic microwave background was invisible until we built radio receivers sensitive enough to detect it. Gravitational waves were invisible until we constructed interferometers precise enough to measure space-time distortions smaller than 1/10,000th the width of a proton. This progression suggests that current forms of cosmic invisibility might not remain hidden forever. Dark matter, which seems to interact only gravitationally, might reveal itself through rare interactions with ordinary matter that future detectors will be sensitive enough to observe. Dark energy, which appears to affect only the largest scales of cosmic structure, might leave signatures in quantum vacuum fluctuations that next-generation experiments could measure. The boundary between visible and invisible is not fixed, but constantly shifting as human knowledge and capability expand. Today's impossibly faint cosmic signals become tomorrow's routine observations. Today's theoretical speculations become tomorrow's confirmed discoveries. The invisible universe of today might become the visible universe of tomorrow. Yet, with each expansion of cosmic visibility comes the recognition of even greater invisibilities beyond. When Galileo first observed the moons of Jupiter, he vastly expanded the known universe, but he also revealed that cosmic reality extended far beyond what anyone had previously imagined. When Hubble discovered the expansion of the universe, he opened infinite vistas of space and time, but he also revealed that most of cosmic history lay beyond direct observation. The pattern continues today.
Each new form of cosmic visibility we achieve reveals hints of even greater invisible realities waiting to be discovered. The detection of gravitational waves has opened a new window on cosmic phenomena, but it has also revealed that the universe contains far more energetic and exotic processes than electromagnetic observations alone could reveal. Recent developments in quantum information theory suggest that information itself might be a fundamental component of cosmic reality, as important as matter and energy in determining the structure and evolution of the universe. If true, much of cosmic reality might consist of information processing and storage operating on scales and through mechanisms that remain completely invisible to current observation methods. The concept of cosmic visibility also intersects with emerging ideas about the nature of consciousness and observation. Some interpretations of quantum mechanics suggest that consciousness plays a fundamental role in determining the properties of physical systems through the process of measurement. If consciousness is indeed fundamental to cosmic reality, then the question of cosmic visibility becomes intimately connected to the nature of mind and awareness itself. These ideas remain highly speculative, but they illustrate how the question of cosmic visibility extends beyond purely physical considerations to touch on the deepest questions about the nature of reality, knowledge, and existence. The invisible universe is not just a collection of hidden cosmic components, but a challenge to our most basic assumptions about what it means to observe and understand. As we continue to explore cosmic invisibility, we must also grapple with the practical implications of our discoveries. The recognition that dark energy dominates cosmic evolution and appears to be accelerating the expansion of space has profound consequences for the long-term future of the universe. If current trends continue, the cosmos will become increasingly empty and cold as galaxies move beyond each other's observable horizons. In such a future, cosmic visibility would gradually decrease as the universe ages. Distant galaxies would disappear beyond the cosmic horizon, leaving future civilizations with an increasingly empty view of space. Eventually, only the local group of gravitationally bound galaxies would remain visible, isolated in an expanding ocean of empty space. This scenario, sometimes called the Big Freeze or heat death of the universe, represents the ultimate triumph of cosmic invisibility. In the far future, most of cosmic reality would be hidden not by physical barriers, but by the expansion of space itself. Future astronomers, if they exist, would inherit a universe that appears almost empty, with little evidence of the rich cosmic structures that exist today. Yet, even this distant future might hold surprises. Advanced civilizations might develop technologies we cannot imagine, capable of detecting cosmic phenomena that remain invisible to our current methods. They might learn to observe dark matter directly, to manipulate dark energy, or to access information from beyond the cosmic horizon through means we have not yet discovered. The question of cosmic visibility ultimately reflects back on our own existence and significance within the vast cosmic context. We are biological structures, composed of ordinary matter, evolved on a planet orbiting an ordinary star in an ordinary galaxy. Yet we have somehow developed the capacity to recognize and study the invisible components that dominate cosmic reality. This recognition is itself remarkable. Through pure intellect and scientific investigation, humans have inferred the existence of dark matter and dark energy, cosmic components that outweigh everything we can directly observe by factors of 5 and 14, respectively. We have detected gravitational waves from black hole collisions billions of light years away, and neutrinos from nuclear reactions in the sun's core. In doing so, we have transcended our biological limitations of our senses and achieved a form of cosmic visibility that extends far beyond what evolution equipped us to perceive. We have become cosmic observers, capable of contemplating realities that span from quantum scales to the observable universe itself. This capacity for cosmic observation and understanding might itself be one of the rarest phenomena in the universe. While stars, galaxies, dark matter, and dark energy exist throughout the universe,
The emergence of consciousness capable of recognizing cosmic invisibility might be extraordinarily uncommon. We might be among the first cosmic structures capable of questioning our own cosmic visibility. If so, the human quest to understand cosmic invisibility represents something unprecedented in cosmic evolution. For the first time in the universe's 13.8 billion-year history, matter has organized itself into structures capable of contemplating the invisible reality that surrounds them. We are the universe becoming aware of itself, questioning its own nature and composition. This cosmic awakening is still in its earliest stages. Human civilization has been studying cosmic invisibility for less than a century. Our most powerful instruments have been observing space for mere decades. We have barely begun to explore the vast territories of invisible reality that surround us.
Yet already, we have achieved remarkable insights. We have mapped the distribution of dark matter throughout the cosmos. We have traced the history of cosmic expansion back to when the universe was a tiny fraction of its current age. We have detected signals from the most violent events in cosmic history and inferred the existence of cosmic components that dwarf everything visible. These achievements represent just the beginning of humanity's investigation into cosmic invisibility. Future generations will inherit instruments and theoretical frameworks that we can barely imagine. They will observe cosmic phenomena that remain completely hidden to our current capabilities. They will answer questions about cosmic invisibility that we have not yet learned to ask. The journey toward understanding cosmic visibility is itself a form of cosmic evolution. Through scientific investigation, we are transforming invisible cosmic reality into visible knowledge. We are converting the hidden universe into human understanding, making the invisible visible through the power of scientific inquiry and technological innovation. This process connects us intimately to the cosmic processes we study. The atoms in our bodies were forged in stellar furnaces billions of years ago. The cosmic expansion we observe is stretching the very space through which we move. The dark matter we infer is gravitationally influencing the galaxy that contains our solar system. We are not separate from cosmic invisibility, but embedded within it, shaped by it, and somehow capable of recognizing it. As you stand beneath that star-filled sky once more, the question of cosmic visibility takes on deeper meaning. You are not just observing the universe, you are participating in its self-discovery. Through your consciousness and curiosity, the cosmos is coming to understand its own invisible nature. The dark matter that surrounds you, the dark energy that drives cosmic expansion, the vast regions beyond the cosmic horizon, all of these invisible realities exist not separately from you, but as part of the larger cosmic context that includes your existence and awareness. The visible stars above you, beautiful as they are, represent only the beginning of cosmic reality. They are lighthouses in an ocean of invisibility, beacons marking the presence of vast hidden territories waiting to be explored. Each photon that reaches your eye carries information not just about the star that emitted it, but about the dark matter through which it traveled, the dark energy that influenced its journey, and the cosmic evolution that made its existence possible. In recognizing cosmic invisibility, you become part of a cosmic awakening that is unprecedented in the universe's history. You are among the first cosmic structures capable of contemplating the invisible majority of reality. This recognition transforms you from a passive observer of cosmic phenomena into an active participant in cosmic self-discovery. The universe is not just around you, it is through you. The cosmic invisibility that dominates reality flows through your awareness, becomes part of your understanding, and transforms your perception of existence itself. In questioning cosmic visibility, you are helping the universe understand itself. This cosmic perspective offers both humility and empowerment.
You are a tiny structure in an almost infinitely vast cosmos, composed of a minute fraction of cosmic matter existing for an instant in cosmic time. Yet you are also a focal point of cosmic self-awareness, a concentration of cosmic complexity capable of recognizing and studying invisible reality. The question, how much of the universe is truly visible, ultimately becomes a question about the nature of awareness itself. Visibility is not just a property of cosmic objects, but a relationship between observer and observed, between consciousness and reality. Through human consciousness, the invisible universe becomes visible in the form of scientific knowledge and understanding. As our instruments become more sensitive and our theories more sophisticated, more of cosmic invisibility will become visible to scientific investigation. Dark matter might reveal its particle nature. Dark energy might yield its fundamental secrets. The cosmic horizon might expand to reveal currently hidden regions of space and time. Yet with each new revelation will come the recognition of even greater invisibilities beyond. The universe appears to be constructed in layers of increasing subtlety and mystery. Each time we penetrate one layer of cosmic invisibility, we discover hints of even deeper mysteries waiting to be explored. This suggests that the quest to understand cosmic visibility will never be complete. There will always be new frontiers of invisibility to explore, new questions to ask, new mysteries to unravel. The invisible universe is not a fixed target to be conquered, but an infinite journey of discovery and wonder. Perhaps this is as it should be. A universe completely visible and understood might be a universe without mystery, without the sense of cosmic adventure that drives scientific discovery and human curiosity. The invisible majority of reality ensures that there will always be new territories to explore, new questions to ask, new forms of cosmic visibility to achieve. Standing beneath those stars, raising your hand toward the infinite mystery above, you now understand that you are not just observing cosmic reality, but participating in its ongoing revelation. The invisible universe that surrounds you is not separate from your existence, but fundamental to it. You are made of star stuff, shaped by cosmic evolution, and somehow capable of recognizing the vast invisible reality that encompasses everything. In that recognition lies both the humility of cosmic insignificance and the wonder of cosmic participation. You are simultaneously nothing and everything, a tiny fluctuation in an almost infinite universe, yet somehow capable of comprehending that very infinity. The invisible universe flows through your awareness, becomes part of your understanding, and transforms you into an instrument of cosmic self-discovery. The question of cosmic visibility ultimately returns you to wonder. In recognizing how little of the universe is visible, you discover how much remains to be explored. In understanding cosmic invisibility, you participate in the universe's ongoing attempt to understand itself. In questioning cosmic reality, you become part of the cosmic reality you question. As photons from distant stars complete their journey by striking your retina, as neutrinos from the sun's core pass through your body, as gravitational waves from ancient cosmic collisions stretch and compress the space around you, you exist at the intersection of visible and invisible reality. You are a conscious node in the cosmic web, aware of both the seen and unseen universe that surrounds and encompasses you. The visible universe, spectacular as it is, represents only the beginning of the cosmic story. The invisible universe, vast and mysterious as it remains, awaits your continued exploration and discovery. In recognizing cosmic invisibility, you become part of the greatest adventure in existence, the universe coming to know itself, through consciousness, through curiosity, and through the endless human quest to make the invisible visible.